Hello, today, this is my fifth video about operating systems. I want to talk about memory management and virtual memory. Last time, I talked about deadlock and semaphore. A deadlock happens when multiple tasks wait for each other and none of them can continue. And a semaphore is a synchronization tool that controls how many tasks can access a limited resource. Until now, I talked about CPU, processes, thread, scheduling, and synchronization. But there is still one really important question left. When a program is running, where is the data actually placed? And what happens when RAM is not enough? This is the main topic today. Memory management means how the operating system manages memory, especially RAM. RAM is a fast-working spatial computer. When a program runs, the program and its necessary data must be placed in memory. The CPU does not usually work directly with data sitting far away on disk. The data should be brought into RAM first, so the CPU can access it quickly. But RAM is limited. We can open a browser, code editor, a music application, and Messenger. From the outside, it feels like all of them are just loading. But inside a computer, all of them needs memory space. So the operating system has to answer questions like this. Which process gets memory? How much memory does it get? Or where should the memory be placed? And what should happen when memory is not enough? That's why memory management is necessary. Without memory management, programs could override each other, waste memory, and crash more easily. Let me start with memory allocation. Memory allocation means giving a certain memory space to a program. For example, when a processor starts, it needs memory for its code, data, heap, and stack. The code area stores instructions, the data area stores global or static area. The heap is used for dynamic memory, and the stack is used for function calls. So when a process runs, the operating system must prepare memory so that the process can work properly. But here, there's an issue about memory space. Memory isn't infinite. RAM has a fixed size. If there is only 8 GB, 16 GB of RAM, the computer cannot put everything there forever. So memory has to be managed carefully. Another problem is fragmentation. Fragmentation means memory becomes broken into small empty spaces. Imagine some memory like a long row of seats. Some programs sit down, some programs sleep, and some empty seats appears here and there. There may be enough total empty space, but if the empty space is divided into many small pieces, a large program may not fit into one continuous space, and this is called external fragmentation. The total free space exists, but is scattered. There is also internal fragmentation. It happens when memory is given in fixed size chunks, but the program does not use the whole chunk. For example, if the system gives 4 KB of space, but the program only needs 3 KB, then 1 KB is wasted inside the chunk. So memory management is not just about giving memory, it's also about using limited memory efficiently. To handle these problems, modern operating systems use an important idea. The idea is paging. Paging means dividing memory into fixed size blocks. The process memory is divided into pages. Physical RAM is divided into frames. A page is a fixed size block from the process point of view. A frame is a fixed size block from the physical RAM point of view. The important point is this. The process does not need to be placed in one continuous area of the RAM. Each page of the process can be placed in any available frame in the RAM, so the memory can be used more flexibly. For example, page 1 can go to frame 7, page 2 can go to frame 3, page 3 can go to frame 10. They don't have to be next to each other. Then how does the CPU find the real location? This is where the page table is used. A page table is a mapping table. It tells the system which page is stored in which frame. In simple terms, the page table works like an address translation map. The process thinks like that its own memory space used, but the operating system maps the virtual address to a real physical address. It's really important. Each process can feel like it has its own clean memory space, but in reality, the operating system and hardware translate those addresses behind the scenes. There's some next important idea: virtual memory. Virtual memory means that a process doesn't have to know the real physical memory directly. It uses a virtual address space. In simple terms, the program feels like it has a large private memory space, but the operating system decides what is really in RAM and what is not. It's useful for two big reasons. First, it protects processors from each other. Second, it allows the system to learn programs even when RAM is limited. Let me suppose that there are two processes, A and B. Process A should not touch process B's memory. If it's possible, one program can easily break another program. Virtual memory can prevent it. Each process has its own virtual address space, so processes are all separated from each other. The second benefit is even more interesting. The system can pretend there is more memory than physical RAM. Of course, this does not mean RAM magically becomes bigger. Instead, the operating system can keep some data in RAM and move some less used data to disk. This area on disk is often called swap space or page file. It's much slower than RAM, but it can help when RAM is not enough. So the basic idea is like this. Frequently used pages stay in RAM. Less used pages can be moved to disk. When the program needs a page that is not currently in RAM, a page fault happens. A page fault means the process tried to access a page, but the page was not in physical memory. At the moment, the operating system pauses the process for a short time. Then it finds the needed page, brings it from disk into RAM, updates the page table, and then the process continues. So a page fault is not always an error. It can be a normal part of virtual memory, but if page fault happens too often, the system can become really slow because disk is much slower than RAM. This situation is stressing. Stressing means that the system spends too much time moving pages between RAM and disk instead of doing real work. For example, if too many large programs are open and RAM is almost full, the program and computer may become really slow. It's kind of terrible. It's not only because the CPU is weak. Sometimes, the problem is that the memory is under too much pressure. The operating system keeps swapping pages in and out, and the actual program becomes slower. So memory management is deeply connected with the overall performance of the computer. Let me compare the important ideas. RAM is a fast working space. Storage is slower, but it keeps data for a long time. Paging divides memory into fixed-size pages and frames. The page table maps virtual pages to physical frames. Virtual memory gives each process its own virtual address space. And page fault happens when a needed page is not currently in RAM. Let me also connect this topic to the earlier videos. In the first video, I said RAM is a workspace of the computer. In the second video, I talked about processes. A process is a running program. Now, we can understand that each process needs its own memory space. In the third and fourth video, I talked about concurrency and resource control. Memory is also a limited resource, so the operating system must manage it carefully. So now, the overall picture becomes more connected. The CPU executes instructions. The scheduler decides which tasks get CPU time. Synchronization protects shared resource. A memory manages to decide how limited RAM is used. Without memory management, programs could not run safely and efficiently. They might override each other, waste memory, or fail when RAM becomes full. Virtual memory can make it much more flexible. It gives each processor a clean memory view, protects processes from each other, and helps the system handle limited RAM. But virtual memory is not free. If the system depends too much on disk, performance can become more slow. So, the input and analysis is RAM is fast but limited. Disk is large but slow. The operating system has to manage both carefully, really carefully. Let me summarize today's idea. Memory management means that the operating system controls how memory is used. Memory location gives memory space to processes. Fragmentation means memory can be wasted or split into small pieces. Paging divides memory into pages and frames. The page table connects virtual pages to physical frames. Virtual memory gives each process its own virtual address space. And page fault happens when a native page is not currently in RAM. In the end, memory management is one of the core jobs of operating system. Because programs do not just need CPU time, they also need memory space. And the memory space must be protected, organized, and used efficiently. So today, I wanted to organize memory management and virtual memory. If I got something wrong, please feel free to let me know in the comments. And I really appreciate you watching this video until the end. Thank you. Bye bye.